So we're in chapter 1 for our week 1. We're going to talk about Introduction to Data by Diaz and other authors of our textbook. We're going to have a lot of definitions and terminologies that we're going to go through. There will not be any formulas in this chapter, so we're going to keep the formulas until next week. And we're not going to use Minitab software this time. So we're just going to take a look at some of the general ideas that we worked throughout the course. So let's begin with the idea of what is a statistic. And I have everything written down here, so we don't have to waste time by me writing things down, and then you just have to sit there and watch me write. It makes it go a little faster. So let's begin with our definition of statistics. Statistics, and now throughout the course, by the way, I try to give you definitions that are sound, accurate, but I try to keep them precise and concise. That means so they're not going to be too wordy and they're not going to be awful long to make notes of. So here's one way you can define what statistic is. I'm going to call it the science of collection, summarization, analysis, and interpretation of data. So by collection, that means that's where you collect your information. That's when you go get a sample. And then summarization means once you get information that you need, you're going to come back and somehow summarize this data in the form of maybe some kind of a table, some kind of a chart, what have you. And then comes the analysis, and here's where the formulas are going to come and help us out. So we're going to analyze the data at hand, and ultimately once we're done with analysis, we would like to interpret the data that we collected to begin with, to address some kind of a concern, some kind of a research problem, or whatever reason was to begin with that led us to collecting this information. Now our terminologies that we talked throughout the course are here. Our first terminology, and this is the idea of a population. Now for population, we're going to call a population the collection of all possible outcomes or measurements on a variable. That's going to be the population. Now the word population, by the way, here, we do not necessarily mean people when we talk about population. We could be, but we may be talking about the population of UPS boxes that are inside the UPS truck. We could be talking about the population of light bulbs, the population of corporations. So we are not necessarily going to talk about people. The word population has stayed with us because initial use of statistic was done by governments around the world to collect census information about the people, counting how many people lived in a certain locale. So the name has stayed with it, but again, it doesn't have its usual connotation, although it could be people, but not necessarily just people. I could be talking about the population of temperatures. So it's pretty broad speaking. The next idea here is that of a variable. So what is a variable? A variable is going to be any attributes, any characteristics that we are researching, that is under the investigation. So I have a few examples of these. For instance, a variable could be, it could be a person's age, it could be a person's income, the price of a house. It could be the GDP for a given quarter, the unemployment rate, weekly, monthly, annually, whatever that rate might be. Or we can talk about the annual income of individuals, corporations, what have you. So that's going to be the idea of a variable. Then we talk about data. Data is any information that you collect on a variable. That's called data. The next definition is that of a parameter. The parameters are numerical values that you actually collect or obtain from the population. Now these numerical values, I have a few examples here, but 3 examples. For example, the average that you calculate for the population, that's a parameter. The standard deviation could be another parameter. Correlation, these are the things that usually we compute or calculate on a population. They call them parameters. Now, these parameters are typically unknown because they belong to a population. And with population, we don't have the entire measurement. So in all likelihood, these parameters will be unknown. And if they're unknown, that means, again, they need to be estimated. And that's what we're going to focus on later on, how to estimate these parameters. There are different ways to estimate them. So our next definition is that of a statistic. Our statistic is going to be, again, numerical values now obtained from the sample. It's just like parameters, right? So statistics, remember, these come from the sample, whereas the parameter comes from the population. So if I calculate the same three items I have up here, the average, standard deviation, correlation, for the sample, then these become our statistics. Okay. Next, since we talked about the sample, so what is a sample? A sample is a representative segment of the population, or a subset of the population. So in this sketch, what I have is, this is the circle of population, and the individual dots here, these are actually the measures on a variable that I'm collecting. So this could be, for example, I don't know, it could be the companies that make up the S&P 500. So I have, let's say, 500 companies in here. Or it could be Russell 2000. I have 2000 companies in here, and each of these dots represent, let's say, the quarterly earnings of each of these corporations. Now, a representative sample is going to be a subset of that. And we assume here, by the way, that the concentration in the population is such that it's pretty much mixed to where I can just collect a representative sample, and the sample participants do actually represent the population. So if I'm, for example, selecting, these are, let's say the dots are now graduate students in all majors. And if my sample here is only looking at the MBA students, well, that's not going to be a representative sample of all graduates from all fields of science. So again, the assumption is that it is truly a representative sample of the population. So the population is pretty well shuffled here. So the sample is going to be a subset of population. Now, being a subset of the population, then the sample has all the attributes, all the characteristics of the population. So that's why it makes sense to work with the sample. Now, why do we need to sample, by the way? Because a lot of reasons. One of them might be because I don't have access to the full population. It could be costly, it could be time consuming, it could be over a very diverse geographic location, and other reasons like that. And sometimes it could be actually detrimental to the population if we want to do population studies. So for example, let's say I want to find out the life of a GE light bulb. If I want to actually test the population of light bulbs rolling off the assembly line, that means I have to light every one of those light bulbs until they burn out pretty much, and then based on that I get information on the life of a light bulb. So, but it doesn't make sense to light up every single light bulb that rolls off the assembly line, because then there's nothing left over to send to the consumers, right? So for that reason, we just simply get a sample. Or if I want to know, for example, the cholesterol level of a person, we don't need to get the entire population of the person's blood. That means drain every single drop of the blood from the person. That would obviously cause fatality, right? So we just get a vial of blood, and then that represents the population of blood that's circulating in a person's body. So anyway, that's the reason we want to sample, to get a snapshot of the population. Now, the variables that we collect, in general, there are two types of variables. These variables could be qualitative or quantitative. Now, qualitative variables, these are typically non-numerical, and they're also called categorical variables. And these are usually attributes. They are characteristics. They are qualities rather than quantities. That's what they're called, qualitative. So example of these could be industry type, let's say retail, energy, financial, technology. These are just sector types, right? Industry types. It could be a brand for something. It could be a brand of clothing, it could be a brand of cosmetics, it could be a brand of luxury purses, it could be whatever, but these are simply names. Or a company name, for example, IBM, Netflix, Google, what have you. So these are all examples of qualitative variables. Now, quantitative variables, on the other hand, these are numerical data. So when we actually collect information on the variable, we're going to collect some kind of a meaningful, genuine number. So these are quantities. And I have an example of those, such as a person's weight, the person's blood pressure, and it could be, for example, the price to earning ratio for a company in a given sector or industry. These are all examples of quantitatives. Now, just because, by the way, we have quantitative information, it doesn't mean that it's a numerical, genuine numerical data that we can actually classify it as quantitative variable. So I've given you 3 examples here. Think about your student ID. Your student ID is really a replacement for your name, true? Or our social security numbers on a broader sense. Every person's social security number is a replacement for that individual's identity. Think about telephone area codes. These are numbers, but it wouldn't, for example, make sense that to say that the average area code, let's say in the county of San Diego is where we live, the average area code is, I don't know, 837. That area code 837 may not even exist. So it just doesn't make sense to do numerical analysis on qualitative information, on these information. Or a student ID. If I say the minimum student ID is 1,000, the maximum student ID is 1,000,000. It's like, so what? That just really doesn't mean anything. Then doesn't mean much. I cannot say, oh, the median student ID is 5,000. The standard deviation of student IDs are 2,000. So these are all meaningless information. Another example would be like zip codes, right? Those are also numerical in nature, but they really don't have tangible values for analysis. Now, if we have valid, genuine quantitative data, quantitative variables, then there are 2 types of quantitative data or quantitative variables. And these are discrete and continuous. Now, discrete, these are the variables that usually end up with a count or a finite value. And there are gaps between numbers, just like gaps on the number line, 1, 1, 2, 3, 4, and so on. And the idea is that there's no continuity. You don't have values that in an interval. So for example, let's say the number of students in this course, the number of students who work full-time in the class, the number of red light photo citations on a given month, the number of homicides. So those are examples of discrete variables, and here I have example of those also. Now think about, let's say the one I have here are the hourly wages. The hourly wages I have, let's say this is for some fast food company, and these are the starting hourly wages. Could be $11.50, $11.75, $12, $12 and a quarter. Now notice these are not necessarily counts, right? So I have here count or finite. So my example of hourly wages fall under the finite values, not the counts, because 11.5 is not a count. It's not a whole number, is what I mean. But these are all finite values. So these qualify as discrete data. And the gap we're talking about between numbers, so you have 11.5, and there's nothing between 11.5 and 11.75. The next number on the number line appears precisely at that discrete point, 11.75, and so on. Another example of discrete data would be the number of, I mentioned, the number of citations issued on a week or in a given week. The number of bankruptcies in a quarter that could occur. That would also be an example of discrete data. Then we go to quantitative variables or quantitative data. Now this one, the quantitative variables are those whose values lie inside an interval or a continuum. Now, inside an interval, so for example, let's say the distance that you travel from work to home and vice versa, from home to work. That distance is a measured quantity, and it is an example of continuous data. So actually, let me here discrete, and I have quantitative. It is quantitative, but let me actually correct this one a bit. What I want to do is this. I would like to actually erase this information right in here, because both of these are quantitative. More specifically, we're talking about continuous, right? So this is a continuous variable, and with continuous variables, again, those are the ones whose values lie inside an interval. Now, typically these are measured, by the way. So if you think in terms of the height of a person, it's a measured quantity, and anything that's measured usually is reported to some degree of accuracy. So when we say, for example, a person's height is 6 feet tall, well, that person may not be exactly 6 feet tall. It's just our measuring devices are calibrated to show it to the nearest inches, let's say. So if you carry enough decimal, that person may not be exactly 6 feet tall. Time, another example here. On the other hand, time is example of continuous variable. Think about time. If you look at, let's say your watch, it shows that the time is, 11:24 p.m. Well, it's going to be 11:24 p.m. for about 60 seconds, true? So 5 seconds later, you look at it, it's still 11:24. But time keeps going on, right? Time keeps moving. It's a measured quantity. So the essence of that variable, intrinsic nature of that variable time, is going to be continuous because it's a measured quantity. Now, how we report these variables, by the way, we could create discrete information out of continuous variables by rounding them. So for example, let's say a person's age. You say, well, I am 40 years old. Okay, well, you're not exactly 40 years old. You were 40 years old at some point in time, right? But you're not 40 years old for, even though, let's say, if you round it to the nearest year, you're going to be 40 years old for about a year, correct? So, but again, the intrinsic nature of variable age, that would be continuous for us. So here I have pretty much labeled how these variables line up. We have two types of variables. We have qualitative and quantitative. And quantitative variables branch off into a discrete and continuous type variables. Now, the reason this is important, by the way, folks, is because it depends on the variable type. What we can do with it depends on whether it's qualitative or quantitative, and what we can do with quantitative variable depends on whether it's discrete or continuous. Okay, now we're done with the variable types. Now we're going to look at actually the data types. That means the data that I'm going to collect. What kind of information could I be collecting? There are 4 data types, as you can see on the screen here in my notebook. We have nominal, ordinal, interval, and ratio. As you move from left to right, by the way, the data type becomes stronger, and stronger means we can do more with it. So let's begin with first talking about, sorry about that. Let's begin with talking about our first type is nominal. Now, nominal data is going to be data that's pretty much a label for the variable. So these values are treated as labels. Like, for example, a person's name, Robert, Mary, Jeff, whoever, whatever the name might be. These are just labels. You cannot really, you cannot find an average name, for example. If you think about the person's political affiliation, that's going to be nominal, right? You have independent, Republican, Democrat, other.
a person religious affiliation is nominal. And typically, by the way, almost all demographic information are nominal types. Now, there's not much, by the way, we can do in the way of analysis with nominal types, as you can see, because all the formulas that we're going to be looking at later on in Minitab, in our own work, these require we have, again, genuine quantitative information that you can actually apply the formulas to. You cannot apply those formulas to the examples I have. For instance, apply the average to a name. Doesn't make sense. Account types. Let's say you have saving account, checking account, brokerage account, and so on. It doesn't make sense to do quantitative work with these. The models of an automobile. Different models of a certain automobile. If you think about the person's gender, for example, here I have 0, 1. Let's say 0 would be male, 1 would be female. Again, these 0, 1s are simply labels for gender. So it doesn't make sense to average 0 plus 1 and get 1/2. So the average gender is 1/2. Now, ordinal data is like nominal, means everything that nominal has, ordinal has. In addition to that, and by the way, nominal data are qualitative, as I have stated here. Just want to point that out just right in here, that these are qualitative. The ordinal data, ordinal is like nominal, except order makes sense now. That's why they're called ordinal. So for example, look at the bond types I have. I have triple B, and then I have A, double A, triple A. These are, let's say, the bond ratings. So I guess it makes sense that the triple A rating bond has a higher value than the triple B bonds, okay, for a certain company or corporation. So order makes sense. Another example of ordinal data would be a person's preference about something, or a person's agreement to on something. You could be, let's say, you could strongly disagree on something. You could disagree on something. You can agree to something or strongly agree to something. So as you go from left to right, from strongly disagree to strongly agree, you have more of an agreement in each level of agreement. So that would be example of ordinal data. So example of these would be ratings or rankings that take place. And an example of this one I made up here is the following. Let's say I have 3 companies here, company A, B, C. And the ranking of these companies by revenue, company A is ranked number 1, then company B is number 2, company C is number 3. And the actual revenues, which is quantitative information here, I have it in billions. Let's say these could be annual revenues. 125 billion, 80 billion, and 70 billions. These are, let's say, in dollars. So if you look at now the difference as you go from 1 to 2 to 3, each of those numbers, right? Each of these numbers as you go from 1 to 2 to 3, the difference between them is 1 unit, right? But if you look at the actual revenue, they're not equally spaced. The difference from 125 and 80, that's $45 billion of difference. Between 80 and 70, that's company B and C. The difference is $10 billion. So distances between them are not the same as suggested by the rankings. So that's what I have written down. The distance between values, when we do ordinal data in general, the distances, we say, are not absolute. So because of that, subtraction and division are invalid operation on these type of data. And these data follow also or fit into the category of qualitative data. That's what these are. Next, we go to stronger level of measurement. Our stronger level of measurement now is going to be interval data. Now, interval data is like ordinal. But the difference is now is that differences are meaningful now, but still we cannot divide. And the other important thing here with interval data is that the position of 0, that number 0, is not absolute. What do we mean by 0 not being absolute? It's not absolute in that it doesn't represent the complete absence of the attribute. So for example, when we say the temperature, and I have it here, when we say the temperature is 0 degrees Fahrenheit, well, that doesn't mean the complete absence of heat. It's going to be awful cold, right? But there is some little amount of heat in there, although for us it's going to be awful cold again. So the point being that it doesn't represent the complete absence of that matter. 0 is arbitrary. Think about time also. My next example here I have temperature and time, the two classic example of these. Now, when it comes to time, there you go. Let's say midnight. Suppose we run on a 24-hour day, right? So at the end of 24 hour, when the midnight strikes, it doesn't mean time ceases to stop, right? Or to exist. So that 0 is more of an arbitrary reference point in our metrics. So that makes this variable interval. So the other thing that remember we cannot do with interval scale data is that we cannot form ratios. So if in one location the temperature is 50 degrees Fahrenheit and in another location we have 100 degrees Fahrenheit, I cannot say that 100 degrees Fahrenheit is twice as warm as 50 degrees Fahrenheit. And indeed, one way you can verify this, if you convert these to let's say international measure of temperature in Celsius or centigrade, you get actually a different ratio. So you can try that. There's a formula for it, but I just don't want to waste your time on that. But if you convert these, you actually get a different point of reference. So for example, the freezing temperature for water in Fahrenheit, that's 32 degrees Fahrenheit when the water freezes. Well, in Celsius, that's 0 degrees Celsius. You see that? So it's a different number. It's not an absolute 0. And the ratio doesn't make sense. Now, then we come to the last form of, our last of our data types. That would be ratio data type. With ratios, again, these are like intervals, but now with ratios, we can actually divide numbers together. And that makes sense. Ratios, remember, ratio is division, quotient. And 0 is absolute. That's important with ratio scale measurement. What do we mean by 0 is absolute? There you go. So let's say you have right now on yourself no cash. You only have a credit card, let's say in your wallet, no cash. So you have $0. Well, that means you absolutely have no money. It's not an arbitrary point. So it's just absence, complete absence of that attribute. And suppose I have $500. The person next to me has $1,000. So for this one now, this person, I can say the person that has $1,000 has twice as much as I do. See, that ratio of 1,000 to 500, the 2-to-1 ratio makes sense. So that's, again, the hallmark of ratio scale measurements. Now, ratio scales are the most powerful measurements or data types. So we would like to have, as much as possible, ratio scale data types. Interval is fine also. A lot of our analysis requires that we have either an interval or ratio. That means and both of these, by the way, interval and ratio, both of these are quantitative data types. And I mentioned that the ratio scale measurement is the strongest data type, and you can do just about everything you want with them, and it would be valid. So that's as far as the measurement data type goes. Now, next we get into our sampling techniques. We actually have two kinds of sampling. So I have them here for you. We could do our sampling with replacement or without replacement. So what's the difference? Well, with replacement is just that. Let's say you select a subject from the population. You record whatever it is that you want to collect of that information. You collect that information, and then you put that person, that subject, that item back into the population, into the pool of available subjects. And then that subject actually has another chance of being selected again. So that's sampling with replacement. So you take the subject, you put it back in. Without replacement, it doesn't do that. It doesn't allow for multiple selections of the same subject. So a subject has at most one chance. So I can only be selected in your sample one time. So let's say you select me in your sample. Then you're not going to put me back in the population and I cannot be selected again. So most of our work, and also going forward, all of our formulas assume that our sampling actually contradictory to what it would make sense to do, that sampling would be without replacement. I mean, after all, let's say, what would you want to sample me twice if you want to measure my weight? You already have my weight. Why do you want to measure my weight 5 times for the same study? So the assumption is going forward later on, it would be this one, that the sampling is done with replacement. Now, part of the reason for this assumption, when we come to it, I'll explain more. But part of the reason is because if you take your sampling, if you do your sampling without replacement, you actually change the probability of selection of the next individual. So for example, let's say there are 10 people in a classroom, and I want to select one person at random. Well, the probability of I select one person at random is going to be 1 out of 10, right? Now, if I put that person back into the pool of available students, again, the probability is 1/10. The next person could be possibly the same person I just selected, but the probability will stay the same, 1/10. If I'm doing my sampling without replacement, the first person has a 1/10 chance of being selected. But once you select that person, if you don't replace, put him back into the population, now the next person, the next student in the class, has 1 in 9 chance of being selected. So if a procedure requires that the percentage in the population should stay at a certain level, then the sampling is done with replacement. But in reality, seldom we do that. We actually do sampling without replacement. Most every time that's the valid sampling. Not valid because they're both valid, but it's the usual sampling scheme is without replacement. Now, when it comes to sampling itself, we have 2 types of sampling. We have what we call probability sampling and non-probability sampling. So what's the difference between them? Well, a probability sample is just that. It is a sample that's drawn in such a way that every element, every member of the population has a chance of being selected. Okay, so there you go. It has a chance of being selected. We are not saying equal chance, we're just saying some chance of being selected. That makes the sample probability sample. For the non-probability samples, where that's not true, it's complement of the probability sample. Not every subject has a chance of being selected. Therefore, these non-probability samples are going to be biased. And if they're biased, we cannot really draw valid inferences to the population. That's the drawback. We can only draw valid inferences or generalizations to the population based on probability samples. So, in our work, of course, we're not going to deal with non-probability samples. What would be an example of a non-probability sample? Here I have our typical mall surveys. So let's say I go to Chula Vista Mall, or if I go to North County Mall, and I participate in a survey. Well, that survey is essentially going to be biased. And the reason is, for example, the people that live in Phoenix, Arizona, or the ones that live in Denver, Colorado, and so on and so forth. They don't have any chance of being surveyed in that mall. In fact, let's say a survey is done in North County Mall. A lot of people that live in South County they have no reason to go to North County, right? So they really don't have a chance of being selected. Now, it could be that mall survey in North County, it could be a valid survey if it addresses, let's say, the subjects, the people that are in that locale within a certain radius, then that would be fine. But you cannot draw it to the general population. So, I have written that down. We only consider probability samples in this course, and that you can only draw generalizations based on a probability sample. Now, we're going to actually look at now different kind of samplings. There's going to be 4 of these, okay? So our first is the most popular one, probably the one you have done yourself, or you have heard about it, or you've known someone who's done this. And these are simple random samples. Now, every one of the samples that we're going to talk about are probability samples. So I put simple random probability sample. But as we go further on, I'm going to drop the word probability. These are all probability samples we're going to do. Now, a simple random sample, or SRS for short, what is this? In a simple random sample, every subject, every measurement has equal chance of being selected. So in this case, we have equal probability of selection. Okay, and that is what a simple random sample is. Now, not only every subject, by the way, every member has equal, but every sample also has equal chance. Okay, so I have every member of the population as well as every sample have equal probability of being selected. So you have the best of both worlds. Equal probability for the sample that was just selected and equal probability for the members of the population. To me, that's the pie in the sky, which seldom actually happens. But how do we actually do this? Well, we can use the table of random numbers, and those are usually at the end of every statistics textbook. Some author has like 1,000 random numbers, and then you can go in a random row and column and start selecting your members or sample participants. Or we can actually draw samples from softwares, like in Minitab, for example. You can actually draw these a random sample from certain population. Now, the simple random sample, by the way, will be the default sampling in this course that we're going to be looking at. Okay, and let's see. The next thing we're going to look at here is a systematic random probability sample. Now, what makes this systematic with systematic random sample? What makes it systematic is that you have a random starting point, and then after your first initial starting point, thereafter you choose every kth element or member of the population. Okay, now this works this works out really nice in the field. So for example, let's say there is a veterinary location, a veterinary office near where I live, and in this location there are, let's say, 1,000 files, 1,000 bills possibly in this location, and I want to know what is the average vet bill in that location. So hypothetically, I made up numbers from 1 to 1,000. Okay, so that's what we have. And then we want to, let's say, choose a sample of size 20. I want to look at 20 cases, 20 folders, if you will, and determine what's the average vet bill in that location. So I need a starting point. Now, my random starting point could be any random number that I like. Or in this case, I made up an example. Let's say I look at the clock and it's 8:53 p.m. So I'm going to actually choose 53 as my starting point on the first record on the shelf. So the first file I'm going to look at is number 53. Number 53, and then in order to have a sample of size 20, because there are 1,000 records here. Now, capital N I have here, by the way. Capital N is the population size for us. Okay, so that's what this is. Capital N, the population size. Little n is going to be the sample size. Okay, and so that's what that is. So if you take the ratio of these two, then that gives me 50. And I put the superscript TH here. So think of that K as your kth. This would be K, right? That's what K is. Let me tidy up that K. There you go. So this is kth record, if you will. So my starting point, remember, was 53 because that's what the time was. And or if you want, you can just keep the hour 8. So start with record number 8. Or if you want, let's say today's, I don't know, April 26th, hypothetical, choose 26 to be your starting point. Whatever random mechanism you want to choose. So we have a random starting point. So I start with record number 53, and then thereafter the 50th record. So the next one would be 103, 153, and so on. Now, what if I start from the latter part of the list? So let's say my first selection, I ask somebody to give me a number. They call out 970. So how am I going to collect a sample of size 20? Well, my first record is 970, right? And I'm looking at every 50th record. So the next one is going to be 50 plus that, right? Which makes it 1050. So what we do is we in fact go in front of the list. You scroll to the beginning. Because remember, there's only 1,000 records on the shelf. So once I go back to the beginning, then I choose the 20th record for my second record. So you have record number 970, and then your 20th record, and then after that your 70th record. See, I'm adding 50 to these, and so on, until you collect your sample. So this is called and in that sense, it's systematic because you get every 50th. That's the systematic part of it. Now, got to be careful with systematic here. I have a couple of examples of kind of data that systematic really doesn't work well with them. So if there are seasonalities, if your data tends to fluctuate in a certain pattern, predictable pattern, then systematic isn't perhaps the best way to do this. You're better off doing a simple random sample. So if you know that seasonalities are exhibited throughout the data, then we cannot use this method. It wouldn't be appropriate. Now these seasonal data, these are like sales data. And the one I have, for example, is, this could be an example of this one, where you have a secular uptrend and there's seasonality in here. This could be, for example, data on the number of passengers that travel on airlines. Okay, under ordinary circumstances. So there is that secular trend in the growth of passengers traveling. And then you have these pronounced up cycle, down cycles, and so on. The up cycle, for example, these could be summer times. These could be during the fall. Again, you go back to summer, and then you go winter time, summer, winter, and so on. So just want to point that out also. And then we look at cluster random sample. Now, in a cluster sample, we're going to divide up the population into subgroups. So that's what I have done in this one. So I have this subgroup. And now how many subgroups you have, it really depends. I just made it into, in this case, 6 subgroups. 1, 2, 3, 4, 5, 6 of them. Okay. Now notice in here, by the way, in the subgroups, I have different colors. But if you note in every subgroup, whatever colors I have, they're the same colors that appear in every subgroups. So in other words, the subgroups are alike. We call these homogeneous subgroups. And then within each subgroup, the subjects are heterogeneous. And that's represented by different colors that you see. So, how does cluster work in here? I'm going to choose a subgroup at random. Now, if you can afford, choose 2 subgroups, 3 subgroups, the more the merrier. So I'm going to choose, let's say, a single subgroup at random. This could be, I don't know, subgroup number 4, right? I'm just making this up. Let's say I'm going to choose this one. There you go. I'm going to select this one. Now, once you select a given subgroup, then you do a complete census inside of that subgroup. In other words, you're going to select everybody in that subgroup, because within the subgroup, notice you have different colors. So we want to make sure that we pick up everyone in that subgroup. Now, we don't necessarily mean people, right? I said every person, but it could be, again, every vehicle. Okay, it could be passenger cars, it could be sports utilities, whatever. Or these could be homes. This could be homes in a zip code, on different streets within a zip code. So I'm going to look at one neighborhood, and then in that neighborhood, I'm going to look at the price of homes in that, let's say, in that city block. Every home in that block. So that pretty much, that's how the cluster sample works. But keep in mind, the subgroups are alike as you go from left to right. So between subgroups, there is homogeneity. But within subgroups, there is heterogeneity. Within means they are different. The last of our sampling methods is this one, the stratified random sample. Now, for this one, if you look at the stratified random sample, just like a cluster, what I've done is I have divided the population into subgroups. Okay, now something that's notably different in this population, I have in each subgroup, the colors are the same. So for example, if you look at this one, right, in this one, every one of these are red. The one, let's say, in the middle, every one of those are light green. To the left of the light green, every one is blue. Okay, so first, the vocabulary of this, the subgroups, we call them strata. So in this partitioning of the population that I've done, I count from left to right, 1, 2, 3, 4, 5. So there are 5 strata in this population. I have 1, 2, 3, 4, 5. So I've divided the population into 5 strata. And then, for example, the one that's in red, this is a stratum number 5, if I count from left to right. So a single subgroup, it's a stratum, the singular word. Now, subgroups are heterogeneous between themselves. As you can see, these are different colors. But within a subgroup, within the strata, right, within the strata, these are the same. So in a given stratum, a single stratum, notice everybody's green here. Notice everyone is blue. So I don't need to collect everybody in this, everyone in here. I can actually get a representative sample of the second stratum, a representative sample from the third stratum, and so on. So we're going to choose a simple random sample from each individual stratum. And here's my example. Let's say in this example, I have partitioned the population into 4 subgroups. The capital N1, that's the population, the total population in the first subgroup, N2, the second population, third and fourth. Now, I want to choose a sample of whatever size. So my sample, I got to make sure that I have representation from the first stratum, from the second, third, and fourth stratum. Now, here I'm making up these numbers. So the first stratum, the population of the first group, 1,000, second 2,000, third 3,000, 4,000. So I just kind of made them like that so the computation is easier. Sigma means the total. Right in here, this notation, this is sigma. What I have here, this is sigma. Okay. So And this is the mathematical, this is the mathematical operator. And I'm trying to clear this up, and it's not letting me erase. Okay, that's fine. So anyway, this is the mathematical operator. This is what we call sigma. This thing is going a little nuts on me. Okay, right in here. Sorry folks, I'm not sure what this is doing. There you go. This is called sigma. This is a mathematical operator. It means the sum of. So this is the sum of n's. That's what this is. And that total is going to be 10,000. Okay, that's going to be the sum. It's going to be 10,000. So let me make this one also nice and readable. 10,000. That's the total of the population. Now, let's say I want to choose a sample of size 400. So how are we going to do this? One thing I don't want to do, because there are four strata here, I don't want to choose 100 from the first, 100 from the second, the third, and the fourth like that. You could do that if the distribution of population is the same. Each stratum, the population size is the same. But if you note here in my example, they're not equally divided. So what would be a fair way of choosing a sample of size 400? Well, in that sample of size 400, the ratio or the proportion of the stratum size, right, the subgroup size, to the total population size, in this case it would be 10%. 10% of the population belong to the first stratum. So I'm going to choose 10% of 400. Sample of size 400 means 40 subjects should come from the first stratum. From the second stratum, the population size is 2,000. So for this one, I'm going to make that again proportional to the size of the subgroup relative to the total population. Twice as many as the first should come from the second, and so on and so forth. Until I have my sample of size 400 this way. Now this is what we call the proportional allocation method for selecting the individual subsamples from each stratum. So here again, I have a notation for you. N is our sample size that we want here. So that's what this is. The sample size N is the sum of individual samples from the subgroups, first, second, third, fourth. Total is 400. And this is called proportional allocation method again. And it's a very popular way of sampling. So there you go. That wraps up our sampling techniques. Now, next we're going to look at the type of statistical studies. We're almost near the end of our video now. Or the lecture, I should say. Now, when it comes to statistical studies, okay, there are two types of statistical studies. We have observational studies and we have designed experiments. So, what's the difference between them? So here's actually the observational study. In an observational study, you simply observe the characteristic and take the measurement or collect that information. That's all you do. You do not interfere or interact with the data. Okay, so for example, let's say I want to know what percentage of the population carries a certain virus. So what I'm going to do is I'm going to observe, let's say 50,000 people, large sample, 50,000 people, and then I'm going to count how many of those actually are carriers of the virus. And if you take the ratio of that, let's say, I don't know, out of 50,000, suppose 1,000 have them. The ratio of 1,000 to 50,000, that would be about 2% of the population that has that virus. So this is an example of observational study. I simply observed the data. I did not conduct any experiment here, right? The data was there. I could afford to observe 50,000 people. Now, in observational data, so this is important for our work. With observational data, we cannot draw causation among the variables of observational studies. We may establish association between, but no causation. Keep that in mind. So, and I will clarify the idea of what do you mean by causation versus association in a minute. The association idea is this. For example, I can say something, for example, the color of a house associates with the price of a house. It doesn't cause the price of a house to go higher or lower, but there's some kind of an association between the price of a house and the color of a house, maybe. So that's the idea of association. Now, that brings us to the idea, the next example is designed experiment, but let me read this last note. Let's see. Okay, it's pretty much what I said earlier. In observational studies, the data already exists and there's no experiment that is conducted. Okay, so let's say I want to know what percentage of men over the age of 60 suffer from acute prostate cancer. So in that case, again, I could go and sample 100,000 men over the age of 60 and look at the incidence of prostate cancer and count how many of those have it and then come out with a percentage. So again, I did not conduct any experiment here. I just collected information on a group of people. So the data is already there. I just have to find time to collect it. Now, in contrast with observational studies, designed experiments are actually the ones that we would like to do. So, with designed experiments, the data is actually created when the experiment is conducted. It's not already there to where I can tap into it. So I have to create some kind of an environment. I have to conduct an experiment for data to be generated. So, here's an example of a designed experiment that I have. Let's say I want to know the effect of oxygen in the fuel on carbon monoxide emission. Okay, so I'm going to measure the CO emission without oxygen additive, and then I'm going to measure again the carbon monoxide emission after the oxygen additive is used. So notice here, the data wasn't already there that I can just collect that data. I have to create some kind of experimental situation. And then what I do is that I apply some kind of a treatment. In this case would be the additive, the oxygen additive. Apply some kind of a treatment to some kind of an experimental unit. For example, could be an automobile. And then look at the effect of treatment on that experimental unit. So that would be a designed experiment, and that is what we would like to do. And you can only draw valid causation in experimental designs, by the way. Now, I have the 3 pillars of a designed experiment here for you. These are the 3 elements that must be present in every designed experiment. 1, randomization. 2nd, replication. And of course, lastly, you must have a control. And you probably have the idea of control, what that would do to our experiment. A control group is a group that does not receive any treatment. They're just the way things are. Okay. So in the field of medicine, the control group are often called the placebo group. You may have heard that one as well. So as long as we have all 3 of these, then we are fine. The idea of randomization is this. Let's say I have 2 groups of people. I can randomly assign them to these 2 different treatments. And replication means repetition of the experiment, that I have to be able to replicate the experiment, means repeat it. And the idea of control I already mentioned. The control group is the group that does not receive any treatment. So in my example of carbon monoxide emission, my control group would be the set of automobiles that do not receive this additive, this oxygen additive. They just receive ordinary fuel. and I look at their emission. See, nothing gets done with the control group. And it is again in designed experiments that we may draw causation between variables, and that's what we really like to do, draw causation. So for example of causation, now I can say that the size of a house in that same location, in that same, say, cul-de-sac, on that same street, the price of a house depends on the size of a house. Or one of the variables would be the size of the house, of course. Could be the age of the house also. But see, I can draw causation there. Now, in my example here I have is, for instance, I can say that the temperature affects moisture content in cakes, right? Here I can draw causation. So temperature is the treatment that's applied to the baking time of a cake. And another example, I can say, for instance, that advertising affects sales. So it's the cause of sales going higher, of course, up to a certain point, right? And here's the reason, because typically, the more you advertise, the more visibility, the more brand recognition, and of course, that could lead to higher sales. So it would make sense to draw causation here. And that's about it. So we covered a lot of ground in this lecture. This should wrap up chapter 1. So hopefully you followed everything that we have done. Please go back to the beginning and review everything that we have done, and hopefully everything makes sense. Again, a lot of definitional, no formulas, a lot of terminologies that we will be using throughout the course. Okay, so again, with that, we are done with our lecture for week 1.